Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, let me introduce myself. My name is Santi Kurniasari with the last 3 digits of my student number is 245. In this video, I will discuss some questions from the midterm exam of the Operation Research course. Before I start the discussions, I would like to admit that I made mistakes in solving some of the questions. I made mistakes in question number 2 and question number 3. In both questions, I was confused about how to correctly handle the constraints that contain equality signs. In question number 2, I forgot to include the constraint into the standard form when converting the problem. And in question number 3, I mistakenly added a slack variable, whereas I should have added an artificial variable for the equality constraint. These mistakes affected the initial simplex table and the final solution. Through this video, I hope to correct and learn from my mistakes. Now, let's move on to the discussions of the equations. Let's move to the question number 2. We'll read the question first. Using the simplex method, determine the minimum value of g equal to 3x plus 5y plus 4z that satisfies the constraints 2x plus 3y less than or equal to 8, 2y plus 5c greater than or equal to 10, 3x plus 2y plus 4z equals to 15, if x, y, and z must be greater than or equal to 0. The question asks us to solve the given linear programming problem using the simplex method. First, I write the general form of the problem. In question number 2, because the form of the problem is a ready-made problem, the general form is the same as the question. Minimizing g and the form of the constraint variable is the same. After write the general form, I write the standard form. First constraint is less than or equal to, so I add slack variable namely S1 to convert them into equation. The first constraint becomes 2x plus 3y plus S1 equals to 8. The second constraint is greater than or equal to, so I add surplus variable namely S2. Since surplus is not a basis, so we have to add artificial variable namely A1. The second constraint becomes 2y plus 5c minus S2 plus A1 equal to 10. The third constraint is already equal equation, so I just add artificial variable namely A2. The third constraint becomes 3x plus 3y plus 4z plus A2 equal to 15. Because this is minimization problem, so the coefficient of the artificial on the objective function is plus n. The objective function becomes gmin plus 4z plus 0s1 plus 0s2 plus na1 plus na2 with x, y, z, s1, s2, a1, and a2 must be greater than or equal to 0. Now I create the initial simplex table. The columns are x, y, z, s1, s2, a1, and a2. The basis variables are listed on the left side. The solution column shows the right-hand side's value. The ZG values is obtained from summing up all the results of multiplying the variable coefficient by the base coefficient. For example, the variable x means 2 times 0, 0 times m, and 3 times m, so the ZG is 3n, and so on. Since this is a minimization problem, I select the k column by finding the largest positive ZG minus GG value. To find the k row, find the smallest positive ratio. I calculate the ratio by dividing the solution and the entry in the k column. If an entry in the k column is 0, I mark the ratio as the type. I perform the pivot operation at the intersection of k row and k column and update the table. Do the OPA and same step as in the initial table. Since all the ZJ minus CJ less than or equal to 0, then the tables are optimum. But there is non-base variable has value in ZJ minus CJ equal to 0, namely S2. Thus, this is minimization case with multiple solutions. Other solution is found by iterating and making the non-base variable whose value in zj minus cj equal to 0 as the k column. In this case is S2. Find the ratio in the same way as before and we will get the k row of this iteration case is the variable of x. The k number is 4 divided by 15. Since all the zj minus cj are less than or equal to 0, then the tabels are optimum. Hence, the optimal solution is achieved with the values of variables as x equals 7 divided by 3, y equals 0, z equals 2, or x equals 0, y equals 0, z equals 15 divided by 4, with the same z minimum equals to 15. Thus, this is a minimization case with multiple solutions. Now, let's move on to question number 3. I will read the question. Using the simplex method, determine the minimum value of c equals 18p plus 12q subject to 3p plus 3q greater than or equal to 24, 2p minus 4q equals 8, 2p minus q less than or equal to 6, with p and q greater than or equal to 0. The question again asks to solve the given linear programming problem using the simplex method. Okay, first the general form of the problem is minimize c equals 18p plus 12q, subject to 3p plus 3q greater than or equal to 24. 2p minus 4q equals 8 and 2p minus q less than or equal to 6. Next, for the standard form, because the first constraint is greater than or equal to, I need to subtract a surplus variable that's minus S1 and add an artificial variable A1. So the first constraint becomes 3p plus 3q minus S1 plus A1 equals 24. For the second constraint, since it is an equality, I just add an artificial variable A2, so it becomes 2p minus 4q plus A2 equals 8. For the third constraint, it is less than or equal to, so I only add a slack variable which is plus S3. The third constraint becomes 2p minus q plus S3 equals 6. And for the objective function, because it is a minimization problem, I add plus m times the artificial variable. So the new objective function becomes v equals 18p plus 12q plus 0s1 plus 0s2 plus na1 plus na2. I create the initial simplex tabel. The columns are p, q, s1, s2, a1, and a2. The basic variable are a1, a2, and s2. Since it is minimization, I select the k column by finding the largest positive value in zg minus cg. To find the k row, I divide the solution by the corresponding entry in the k column. If the entry is 0, I mark the ratio as a dash and it will not be considered. The row with the smallest positive ratio is the k row. In this initial tabel, the k column is p, the k row is S2, and the k number is 2. After that, do the pivot operation. It's at the intersection of the k column and k row. Do as before, to calculate zj, we multiply the coefficients of the base variables by the corresponding entries, and then sum them column by column. Have the k column is q, the k row is a1, and the k number is 9 divided by 2. Since all the zj minus cj are less than or equal to 0, then the tabels are optimum. Hence, the optimal solution is achieved with the values of variables as p equals 14 divided by 3, q equals 10 divided by 3, and z minimum equals 124. But there is still an artificial variable that exists and its value is greater than 0, namely a2 equals 12. Thus, this is a minimization case with no solution. That concludes my discussion of the midterm question that I answered incorrectly. Thank you very much for your attention. I apologize if there are any mistakes in my explanation. Wassalamualaikum warahmatullahi wabarakatuh.